Hello everyone. In this second lecture on inverters, we'll be learning about three-phase inverters from single voltage source. We'll be seeing how the voltage waveforms of line to line and line to phase voltage changes, and what are the frequency components that get involved when we design a single voltage source full wave three-phase inverter. Now let us look at three-phase square wave inverters. Three-phase square wave inverters, there are 6 switches involved, and there is one voltage source or VDC, and there are 6 switches involved, and the switching pattern is like this. If we remember the rectifiers, three-phase rectifiers, we had similar type of switching pattern, 180-degree conduction method for switch 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7, and here our firing angle alpha is equal to 0 degree, as we can see, and the switching pattern is almost same or similar to what we had in the rectifier. So we know how it works. So first 60 degree, we can see that switch 1 5 6 are active. For next 60 degree, that is from 60 to 120 degree, we have 1 2 6 are 6 active. Next we have 1 2 3. Next we have 2 3 4. Next we have 3 4 5, and next we have 5 6 4 5 6 4 5 6 on. So in 60 degrees interval, our switching pattern changes, and this switching pattern actually changes the actual output of it. We see how. Let us look at how the circuit is implemented. Here we have 3 half bridges, that is 3 these kind of series MOSFET configurations, and from the middle of it we connect one resistive load, and from the middle of the second part we connect the second resistive load, from the middle of third part we connect the third resistive load. All the resistors are connected to a point called a point which is the neutral. So we get 3 phase results. Now from 0 to 60 degree, we have already seen the switch 1 5 and 6 are active. The switch 1 5 6 are active. This is shorted, this is shorted, and this over here is shorted. If this path is shorted, what are the path of current? The path of current can be this, through this direction it reaches the neutral, again through this direction it reaches the neutral, and from the neutral to this direction it reaches a negative. That is, from the positive side of the voltage source it goes to phase A through a resistor to the neutral. So it goes to phase A through a resistor into this point is neutral. This resistance is R. Again, from the positive side of the voltage source it goes to phase C through a resistor into neutral. So here we have a phase, we are considering phase C through a resistor, it goes to the neutral, and from the neutral it goes to a resistor to phase B and goes to the negative of the voltage source. So here we have a resistor which goes to the negative of the resistor. Here we have phase B and the resistance is R. Now VAN would be equal to VCN since they are parallel, and this would be equal to, since these two resistors are parallel, the equivalent resistance of them would be R by 2, and the total equivalent resistance would be R by 2 plus R into VDC. So this becomes R by 2 into 2 by 3 R VDC is equal to VDC divided by 3. So we get VAN is equal to VCN is equal to VDC divided by 3. Now what would VBN be? VBN would be minus R divided by R by 2 plus R VDC. Now why the minus sign? This is because current flows in this direction. current flow starts from the positive and ends to the negative. Current flows in this direction, but the voltage we are considering is in the opposite direction. So current flows from minus to plus, and as a result the output voltage is negative. The resistance across this path is R, and the total resistance is R plus R by 2 VDC. So we get minus R into 2 by 3 R VDC, that is minus 2 by 3 VDC. So we get VAN is equal to VCN is equal to VDC by 3, and VBN is equal to minus 2 VDC by 3. Now when we move from 60 degree to 120 degree, switch 1, 2, 1 and 6 are closed. Switch 1 is here, which is closed. Switch 2 is here, which is closed. Switch 6 is here, which is closed. These 3 switches are closed. If these 3 switches are closed, the equivalent circuit becomes, here we have node A. To node A we go into resistor R and reach the neutral. From the neutral through resistor R we go to phase B and the negative of voltage source. Again from the neutral to this path we go to phase C. So for easier remembrance, we can say that when the switches at the upper side are on, then the current flows from the positive side of VDC to the load, and when the switches to the load to the neutral, and when the switches at the bottom part are on, the current flows from neutral through the load to the negative part of VDC. Here we have C. So here we can see VBN is equal to VCN is equal to, calculation is similar to the calculation that we had, but the current flows in this direction. You will have minus VDC by 3, and VAN would be VDC to VDC by 3. The calculation of resistance is similar to the calculation we had from 0 to 60 degree. From 120 degree to 180 degree, switches 3, 2 and 1 are closed. So here we have switch 1, here we have switch 3, and here we have switch 2. So how the equivalent circuit maps out? The positive is connected to A and B, so we have 2 resistance going to the neutral, and the negative is connected to C. So this will be C, this will be B, this will be A, this will be our neutral, and here we have our resistances R. Again here VAN would be equal to VBN. Calculations are similar. The voltage would be VDC by 3, and again VCN would be equal to minus 2 VDC divided by 3. If you have understood the calculation from 0 degree to 60 degree, there should not be any problem in understanding this calculation. This negative sign is present because the current flows in this direction, but VCN we have taken this convention of voltage. So we get VAN is equal to VBN is equal to VDC by 3, and VCN is equal to minus 2 VDC by 3. Now 180 degree to 240 degrees, switches 4, 3 and 2 are on. This switch and this switch are on. So equivalent circuit becomes phase B. From the positive we have only phase B. From the negative we have phase A and C. All the phases ultimately reach the neutral. So VAN is equal to VCN is equal to, as this is in the negative side, minus VDC by 3. Why is it VDC by 3? Because 2 resistance are here in parallel, and VBN would be 2 VDC divided by 3, because there is a single resistance involved, they become parallel and it is connected to the positive side. For the next 60 degrees, switch 5, 4 and 3 are on. We have switch 5 here, switch 4 here and switch 3 here. So with the positive we have phase B and C connected, and with the negative we have only phase A connected. if we draw the equivalent circuit, with positive we have phase B, we have phase C, and with negative we have phase A, and all of them are connected to the neutral. So VN is equal to VCN is equal to VDC by 3, VAN is equal to minus 2 VDC divided by 3. For the next 30 degrees, switch 6, 5 and 4 are on. This is switch 6, this is switch 5, this is switch 4. The positive is connected to phase C. This is our phase C, and the negatives are connected to phase B and A. They are all connected to the neutral at the other end. So, by similar convention, VAN is equal to VBN is equal to minus VDC by 3, and VCN is equal to 2 VDC by 3. Now we can look at the voltage output that we get from this kind of inverter. From 0 to 60 degree, let us just look at VAN. 0 to 60 degree, we have got VAN is equal to VDC by 3. Next 60 to 120 degree, we got 2 VDC by 3, and next stage also we got VDC by 3. From 180 degree to 250 degree, we have minus VDC by 3, then we have minus 2 VDC by 3, then again minus VDC by 3. So we have calculated we have made all the calculation in our earlier slides, and we have plotted those calculations, and we get graphs similar to this. We can see that the graphs are closely resembling to sinusoids, but not actually sinusoids. And again, we can see that here we have VAN, VBN, and VCN. All three are shifted, similar sort of shape, but they are shifted in terms of phase by 120 degree. Now, as we can see, this is our line to neutral voltage that we have derived. From this line to neutral voltage, we can actually measure the line to line voltage. How can we do that? We can do that by, let's see, VAB would be VA minus VB. So from 0 to 60 degree, VAB is equal to VDC by 3 minus 2 VDC by 3. So we get VDC. So from 0 to 60 degree, VAB is equal to VDC. From 60 to 120 degree, we have VAB is equal to 2 VDC by 3 minus VDC by 3. So from in this stage we get VAB is equal to VDC. Again we get VAB is equal to VDC. For the next 30 degree, we have positive VDC by 3 as VA and positive VDC by 3 as VB. These two get cancelled out and we get output is equal to 0. For next 30 degree, we get negative VDC for VA and positive 2 VDC by 3 as VB. If we subtract these two, we get minus VDC, and again in the next stage 2 we will get minus VDC. So the line voltage can be determined from the phase voltage itself, and the curve of the line voltage would look something like this. Now, if you want to perform the Fourier analysis of line to neutral voltage, we see that the line to neutral voltage is anti-symmetrical, and this is completely AC. There is no DC component involved. So from that we can write A0 is equal to 0, summation of AN sine AN cos omega t is equal to 0. So only component that is V output would be summation of Vn cos Vn sine omega t, omega n t. Now Vn, as we have learned, 2 by pi integration of 0 to pi V sine n theta d theta. By modifying it, we will get 2 by pi from 0 to pi by 3. we get VDC by 3 sine n theta d theta plus integration of pi by 3 to pi by 3. We get 2VDC by 3 sine n theta d theta plus from 2 pi by 3 to pi VDC by 3 sine n theta d theta. So again this can be written as 2 by pi, your bracket start, v let's convert into second bracket, VDC by 3 n minus cos n theta 0 to pi by 3 plus 2VDC by 3n minus cos n theta pi by 3 to pi by 3 plus GDC by 3n minus cos n theta 2 pi by 3. Fine. So we are dividing it into 3 components. First component for first 60 degrees, second component for next 60 degrees, and third component for the next 60 degrees. Okay. Now the 3 components, we have to resolve the 3 components, and we are bringing out the VDC by 3 outside. So by bringing that out, we get 2 VDC by 3 in pi cos 0 minus cos pi by 3 plus 2 cos n pi by 3 plus 2 cos n pi by 3 minus 2 cos 2n pi by 3 plus cos 2n pi by 3 minus cos n pi. So it becomes 2VDC by 3 pi n. Cos 0 is equal to 1. Cos 0 is equal to 1 minus cos n pi. Then we have plus cos n pi by 3 minus cos 2n pi by 3. So we get VAN that we have been measuring is equal to summation of 2VDC by 3 pi n 1 minus cos n pi plus cos n pi by 3 minus cos 2n pi by 3 sine 2 pi f t 2 pi f m t. This is the value of VAN that we get. So from here we can see that the output voltage VAN is largely dependent on the value of N, or the value or the frequency component involved in it. And we'll get both higher frequency components and lower frequency components, and from this term, which is a constant term over here, we can see as n rises, the value of VAN falls, and as a result, we'll get the uh, we'll get the maximum value at fundamental frequency, and as the frequency rises, the value actually will decrease from time to time. Now if you look at the line to line voltage, we see that this is actually not antisymmetric. The output is like this, but if we shift it by 30 degree, we get our 0 here, we get 30 degree here and minus 30 degree here, and as a result, by shifting it by 30 degree, we get it antisymmetric. Our calculation becomes a lot easier if the wave shape is antisymmetric. So we are going for the calculation, we are going to shift it by 30 degree. As a result, when we are considering PAB, our A0 will be 0 because this is purely AC, and summation of AN cos omega nt is equal to 0 because we have made it into antisymmetric. Only factor that will be effective is the Bn factor. We have found Bn is equal to 2 by pi integration of 0 to pi the output sine n theta d theta. So we can write it as 2 by pi integration of pi by 3 to pi by 6, that is 30 degree to 150 degree, pi by 6 to pi minus pi by 6. In this range, the output VAB is equal to VDC sine n theta d theta. So we can write 2 VDC by n pi minus cos n theta. This is from pi by 6, pi minus pi by 6. It can be written as 2 VDC by n pi cos pi by 6 minus cos pi minus pi by 6. Now cos A minus B is equal to cos A cos B minus sin A sin B. From that we get to VDC by n pi cos pi by 6 minus cos, in all these cases there will be n pi by 6, there will be an n involved, minus cos n pi by 6 plus sin n pi by 6. Now since n is an integer, in any case sin n pi will be equal to 0, and we'll be left with just this term and this term. So we get Bn is equal to, we'll get Bn is equal to 2 VDC divided by n pi cos pi by 6 minus cos n pi cos pi by 6, cos n pi by 6. From there we can write 2 VDC divided by n pi cos n pi by 6. We are taking n pi cos n pi by 6 as common, 1 minus cos n pi. Now if n is odd, cos n pi would be is equal to minus 1, and 1 minus minus 1 would be is equal to plus 1. So if n is odd, this term will become 2, and we'll get Bn is equal to 4 VDC by n pi cos n pi by 6. Again, if n is even, we get this term as 1 minus cos n pi by 6 is cos n pi by 6 would be equal to 1, and 1 minus 1 would be equal to 0. We will get Bn is equal to 0. From there we get VAB that we have been measuring is equal to summation of summation of 4 3 DC divided by n pi cos n pi by 6 sine 2 pi f n t minus pi by 6. Why we're writing here minus pi by 6? Because we have shifted whole curve by pi by 6 degree. Minus pi by 6, and this is true when n is odd. So by Fourier analysis, we can see we will get the fundamental frequency, and all the frequency component will be below the fundamental frequency. We will only get the frequency component of f, 3f, 5f, and so on. We will not get the even harmonics in case of in case of line-to-line voltage of a three-phase single voltage source inverter. Thank you so much. That's it for this lecture. In the next lecture, we'll be learning about a very useful inverter for practical purpose, which gives the output voltage quite similar to sinusoids. That is a resonant inverter.